Hey guys, let's jump into our next section, 2.5. Pull it up. So we had our introduction to limits, got familiar with them, did a lot of different type of limit questions, then kind of took a pause, did the precise definition of the limit. It was kind of almost a standalone section. And now we're going to pick up where we left off in 2.3 with this idea of continuity. And that's going to be a key element to building up to defining the derivative here at the end of our chapter. So let's define continuity, or what it means to be continuous. F of x is continuous at x equals a if the limit of f of x as x approaches a is equal to f of a. So what we're saying here is that the limit value has to equal the function value at the same location. I think this is much better described in a graph. What is continuous versus what is not. So I'm going to show you guys lots of different pictures, and we'll just kind of try and figure out, like, is it continuous right at this location? So here we're only looking at x equals a. We see that graph, it's got a jump happening at a. Just kind of based on your intuition and the name continuous, does it seem like this function is continuous at a? And just the name continuous, you look, well, there's a jump there, so there's a break. Seems like that would not be continuous, and that's absolutely right. No, this situation would not be, f of x would not be continuous at a. Why? And here's where we can kind of go a little deeper and look at that definition of the limit having to equal the function value. Well, in the case of a jump, right, the limit does not exist. What's happening on the left does not line up with what's happening on the right. The left side is going to one y value, the right side is going somewhere else. So that limit, if the limit doesn't exist, well, certainly it cannot equal the function value. In this case, we see the filled in dot, that's where the function value would be. But if the limit does not exist, certainly they can't equal each other. We're going to call this type of situation a jump discontinuity. Makes sense. There's a jump. Looks good. Okay. So if there's a jump, it's not continuous. All right. How about if there's a hole? So here at A, we see there's this one point that has been taken out or removed, leaving a hole there. Would we say that this function is continuous at A? And well, right, even though that hole is infinitely tiny, there's still like a break in the function. And so no, this would not be continuous either. Let's kind of look a little bit closer and see what's happening. The limit here does exist, right? The left side is going to the same place as the right side. We have the answer to the limit when there's a hole. But in this case, f of a does not exist. It's the other part that's a problem. There is no point there. We're going to call this a removable discontinuity because literally that one point, it's like somebody reached in and grabbed it and removed it from the function. So you might think, okay, the limit existed, but not the function value. What if we just altered this picture just slightly? What if there's still a hole there at A, but it's actually, that point is actually located a little bit higher maybe? Would that be continuous? Now the function value does exist. It's just not at the same spot as the hole. Well, no, that's still a break in the function. We're still going to call this a removable discontinuity because, again, it's like that point has been removed, although it's almost like it's been relocated in a sense. Now the limit exists and the function value exists. It just so happens they don't equal each other. So that's not good. We're getting better though. We're getting closer maybe to continuity. At least they both exist. Okay. So we're still going to call that a removable. All right. How about this case? What's happening? So we've got a vertical asymptote happening at x equals a. Do you think that's continuous? Definitely not. There's a huge jump. It's almost like an infinite jump there. This going to infinity, this to negative infinity on either side. No, that's not continuous. If there's a vertical asymptote at a, that's not going to work. We don't really need to say anymore. In this case, the limit would not exist because they're on opposite ends. But, even if, this was pointed up in this direction, still, there's going to be that break in the function at that point. If there's a vertical asymptote at x equals a, not continuous, we're going to call that an infinite discontinuity. So we've got these three types of discontinuities: the jump, the removable, and the infinite. And now finally, we can look at something that doesn't have any of these features. What if the function, just kind of goes through and there's nothing unusual at a, the point is where it's supposed to be, there's no jump, there's no hole. Would that be continuous? And yes, finally it is. That's what we'll call continuity. Nothing unusual. The function just kind of goes about its business and the point is where it's supposed to be and all of that. Then if you look closer, yep, it would be. This is the only time where the limit as x approaches a for the function would equal the function value. The limit from either side is going to that y value and the function value is there at the same spot. So we have continuity. Okay, very cool. Let's look at a couple more examples. One is going to be done graphically, and two more, we don't have the graph. For all these, we're going to state all the x values where f of x is discontinuous, kind of look at it from that side. And then we'll state the intervals where f of x is continuous. So part A, we've got this graph. Okay, very good. I'm going to switch over to my paper here, but I realized I did not copy this graph just yet. So I'm going to do that now. I think we have about 5 tick marks in each direction. And I'm going to try and recopy this quickly. Okay, almost done. All right. Okay, let me switch cameras. Here was part A. Again, we're going to state all the x values where f of x is discontinuous, and then state the intervals where f of x is continuous. So let's start with, what are the x values where we're discontinuous? And we'll even name which type. So as we kind of go maybe left to right, we can see, hey, right here at -4, there's a break, there's a discontinuity. Which type is that? Well, if there's a hole, even if it's relocated somewhere else, that's a removable discontinuity. Okay, as we keep going, well, here the point is there. No problem. We get to x equals 1. And what's happening? There's a jump. In this jump, there's a hole for both sides. You know, I think in the example we saw earlier, one of them was filled in. It's still a jump. And if we keep going further, x equals +4, there is another removable. And the point is not relocated somewhere else, but that's okay. Still a removable. We got it. All right, so if these are the locations where there's a discontinuity, then what are the intervals where f of x is continuous? Well, basically everywhere else. So every other point on the path, skipping those 3 locations, it is continuous. So let's say f of x is continuous. It's going to be continuous from -infinity up to -4. Then maybe we say union from -4 to +1, skipping over 1, union from 1 to 4, and then union 4 to infinity. So it's like 4 sections, 1, 2, 3, and 4. Right, so, okay. Now it gets a little bit more challenging when you don't have the graph, right? So here was part B. F of x equals x minus 3 over x squared minus 2x minus 3. If we don't have the graph, again, we're kind of still thinking to ourselves, like, where are there holes? Where are there jumps? And even where are there vertical asymptotes? Where might those occur? Well, those would all be places where our function is undefined. So we're going to ask, where does the denominator equal 0 if we have something like a rational function like this one? So if we investigate that, where would the function be undefined? Well, when the denominator is equal to 0. In this case, x squared minus 2x minus 3, to solve this, we'll factor. Let's see, how would that work? X minus 3, x plus 1. We'll do it. So then we can set both factors equal to 0 and realize, okay, x equals 3 and x equals -1. But now, once we know where the denominator equals 0, that's great. It's going to be discontinuous at both these locations. But we want to go even further than that. We want to know which type of discontinuity would occur, and we can figure that out too. Let's think. I think I need a new piece of paper here to continue. Here's what we can do. Take the limit as you're approaching each one of these for our function. What would happen with the limit as x approaches 3 for our function x minus 3 over x squared minus 2x minus 3? If we tried to plug in what would happen? 3 minus 3 over 3 squared minus 6 minus 3, 0 over 0. Hey, if it's 0 over 0, then what's going on there? A hole, right? Aha, If it's a whole, we know that it's removable. How about that other x value, -1? What would plugging in do? -1 minus 3, -1 squared, plus 2 minus 3, -4 over 1 plus 2 minus 3, 0. Hey, what happens when we have something other than 0 over 0? That's a vertical asymptote. So we know at x equals 3, there's a discontinuity and it's removable. And at x equals -1, there's a discontinuity and it's an infinite because of the vertical asymptote. Very nice. If these are where it is discontinuous, then where is our function continuous? Well, everywhere else. So -infinity to -1, union from -1 to 3, union from 3 to infinity. We could take a look at the graph really fast. It's always recommend, always enjoy it. X squared minus 2x minus 3. Okay, so we see that vertical asymptote. We can even graph the vertical line, the vertical asymptote, and the vertical asymptote there at x equals -1. And there's also a hole at 3. See if we can pinpoint that. There we go. So the infinite discontinuity and the removable discontinuity, kind of cool. All right, we got one more, part C. Part C, this is interesting. This was a piecewise. G of x equals 1 minus x when x is less than or equal to 0, and e to the x when x was greater than 0. Okay. When it comes to a piecewise function, if you look at each individual piece, there's no problems, right? 1 minus x, right? You're never dividing by 0. You're never undefined, right? E to the x, same thing. This is always defined on its domain. So there's no discontinuities on each individual piece in this case. But what about where they come together? The question is there a jump at x equals 0? Does this side, when you approach 0 from the left, line up with how you approach 0 from the right? Let's take a look. The limit as x approaches 0 from the left for g of x. If we approach from the left, we're going to use values a little bit smaller than 0. All right, so we're going to take the 1 minus x. As it approaches, well, to find this limit, we can simply plug in and we get 1. All right. Okay. How about as we approach 0 from the right? Well, from the right side, we want values a little bit bigger than 0, so the greater than. We can, again, simply plug in 0 to this, e to the 0. Hey, what does e to the 0 equal? Well, anything to the 0 is 1. And look at that. They're the same. So we know that the limit as x approaches 0, the two-sided limit, is equal to 1. It does exist. No, there's no jump. Those two match up, and we got 1. Okay. Now that we know there's not a jump, is it true that the limit is equal to the function value? What is g of 0? Because now that limit value has got to equal the actual function value. Let's see, g of 0, that's where we would equal 0. We got the equal sign. So we're going to use the 1 minus x. And again, well, we get 1. So it's kind of surprising, you know, we thought maybe the piecewise there would be a jump, turns out no, and in fact, even the function value is the same. Since these are equal, this is continuous even at x equals 0. No discontinuities. And if we thought about the interval where it's continuous, well, it's everything from negative infinity to infinity. Let's graph this really fast. I think it'll all come together. Let's see, we got y equals 1 minus x, where x is less than or equal to 0. Okay, we got that line. We also have y equals e to the x, where x is greater than 0. And there you go, the two sides line up. They both go to 1 from the left and from the right. And in fact, the point itself is right there at 0, 1 due to the green line being an or equal. So there's not even a removable discontinuity. It's continuous all the way through from negative infinity to positive infinity. Okay, guys, let's stop this video here. We'll pick it up in the next one.